Hi folks, welcome back. And before I get into anything else, I was just talking to my son about how I got his shirt on today, so I was gonna have to give him a plug. My oldest, this is Grim Tales, is my oldest son's company that he recently started for video game development, and he's got some very exciting things going on with that right now. And then my youngest son, he just passed his um, private pilot license test. So he is now a licensed private pilot. So we got some cool things going on in our family right now, and I give you all that for free. I won't charge you any extra for it. But back to this now, back to DNA. In the last video, I talked about all the problems evolution has with the massive amount of information that DNA has. So now in this video, I want to go on to explain the reasons why the essential structure of DNA also is a death sentence for evolution. And this discussion will undoubtedly take several videos. I have no idea how many. We'll just see how long it takes. But what I'll do is I'll pick a few aspects in each video that I will highlight to discuss there. And in this first one, before I get to talking about that, the first thing I need to do is explain to you some of the basics of the structure of DNA. So I'm going to start this video doing that. So DNA was discovered in 1953, and when it was heralded as the discovery of the language of life. And all the research the past, 7 decades have indeed proven this to be the case. DNA is in fact the language of life. DNA is made up of only 4 building blocks, which are called nucleotides. And if you look at this slide, I'll show you what a nucleotide looks like in 2D. First of all, each nucleotide is composed of carbon, nitrogen, hydrogen, oxygen, and phosphorus atoms. That's what each of the C's, N's, H's, O's, and P's are. And each nucleotide contains a nitrogenous base, meaning it contains nitrogen, a sugar, in this case is called deoxyribose, and a phosphate group. A nucleotide can have 1 to 3 of these phosphate groups, and here's what it would look like if it had 3. See here, we got 1, 2, 3 of those groups, right? But when it's incorporated into DNA, it only has 1 phosphate group, like this guy does. And incidentally, this deoxyribose ring structure tells us how DNA got its name. In a typical ribose sugar, there's an OH right here, next to that other OH, in this spot that's called the 2' position. And that's what you would find in a molecule like RNA, which we'll talk about later on. But DNA is missing the O there. It doesn't have an OH, it only has an H. So it's missing the O, it's missing the oxygen in this 2' position. So it's without oxygen, or it's deoxy. So it's a deoxyribose. And so DNA got its name to be deoxyribonucleic acid, or DNA. And you know, I'll give you this information for free too. I mean, I'm just giving stuff away today. But now back to this. All the atoms in the nucleotide structure are held together by covalent bonds. A covalent bond is the sharing of electrons between atoms that results in a stable balance of attraction and repulsion between them. So it's an attractive force that holds 2 atoms together, and it's actually a strong attractive force. And all these single lines on here, there's one, all these, right? All these single lines. Here's some over here, right? they all represent a single covalent bond between the indicated atoms. But you can have more than one. So all these guys where we got double lines, yeah, here's one over here, right? All those double lines represent a double covalent bond between those two atoms. Oh, and incidentally, another place where lines join, but there's no atoms listed there, that's where you'll find a carbon. So like there would be a carbon, there would be a carbon, there, up here, here. They just don't draw all the carbons in just to make it a little bit easier in the structure. I'll give you that for free today too. Man, this is a great day. And there are 4 nitrogenous bases, which create the 4 different nucleotides. So here I'm showing each of their structures in 2D. Their names are adenine or A, guanine or G, cytosine or C, and thymine or T. The 4 nucleotides, the A's, G's, C's, and T's, make up the 4 letters in the alphabet of the language of DNA, or the language of life. Now notice that 2 of them, A and G, have a double ring structure. So I'm talking about that right there and that right there. Same thing here and here, right? They have double ring structures in the A's and G's, while the C's and T's, see, they just got the one. These guys down here, they just have 1 ring structure. And this is significant in the pattern of how DNA is bonded together, which we're going to get to in a moment. And let me just point out here, by changing the base attached here, right, through this bond here, by changing the base that we have attached here, that's how we make the 4 different nucleotides. So you swap that position out for any of these other guys, and then we end up changing to one of the different nucleotides. Now this image, another 2D image, is of a very small piece of DNA. And notice we have 2 strands here. This would be considered one strand, and this would be considered the other strand. And the overall appearance we get is that of a ladder. And these bases would make the rung. You see that? And this image is also if we took our DNA and laid it flat. So it's not twisted up in its helical shape in this 2D image, okay? And then we have the sugars and phosphates creating the vertical backbone part of the ladder. And then the bases are sticking out in the middle, creating the rungs. So in the backbone, we have alternating sugar, phosphate, sugar, phosphate. See that? And in the rungs, we have the bases, G's and C's, right? And then A's and T's bonded together. Okay? And notice how on the one strand, let's look at the A, it's base pairing with the T on the other strand. And then G is base pairing with the C on the other strand, right? So this base pairing in the middle happens with hydrogen bonds. And I'm showing the hydrogen bonds as those dots and dashes right there. Okay? So the base pairing happens with hydrogen bonds. And hydrogen bonds are not as strong as covalent bonds. And so remember, all the other bonds in the rest of the molecule are all covalent bonds. A hydrogen bond is the interaction of a hydrogen atom and electronegative atom, like a nitrogen or oxygen. The hydrogen must be covalently bonded to another electronegative atom to create the hydrogen bond. So electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. Basically what it means is the stronger your electronegativity is, the stronger you're going to pull electrons. And so if we look at A and T, notice how they are bonded with 2 hydrogen bonds, and G and C is bonded with 3 hydrogen bonds. So the G and C base pairs would be 50% stronger than A and T because they have one more hydrogen bond than A and T does. So please get this. I cannot stress this enough. DNA is basically two covalently bonded molecules held together in the middle by hydrogen bonds. But the hydrogen bonds aren't nearly as strong as the covalent bonds found throughout the rest of the DNA molecule. This is absolutely critical to understand. Okay, with that cursory explanation of nucleotides, let's talk about how they're arranged to build the DNA molecule. And the analogy that I want to use to help you visualize this is that of a ladder. First of all the nucleotides are covalently linked to one another over and over again to form a long strand of DNA. And a good analogy for that is Legos. So I got some Legos here. We get to play with Legos again, right? Just like Legos get attached to one another, right? Over and over again. The 4 nucleotides would be attached to one another in long strands, okay? So each one of these gets attached to the previous one, right? The front goes to the back, so to speak. And when you're done building your DNA, there can be millions to billions of these covalently linked together, depending on the size of the genome and the number of chromosomes, which we'll get to in one of the later videos. And in this arrangement, you end up with, I got some other ones here, you end up with the sugar and phosphate groups in the backbone of the ladder and the bases forming the rungs of the ladder perpendicular to the backbone. So now if we look at these, so each one of these now is a nucleotide. Then I even put some letters on it, so this would be G, right? So this would be the backbone, like sugar and phosphate. This would be the base sticking out. And then you take one nucleotide and it would be covalently attached to another one, like that. Okay, so then these would all be, we put some more on here, a long strand of these, depending on the size of the chromosome and the genome as to exactly how many there were. But here's the thing. DNA is not just one long strand of DNA. DNA is actually 2 strands of DNA that are joined together. And the uniqueness of the DNA structure and the essence of life itself is portrayed in how the 2 strands are held together. So let me show you this here. The two separate strands of DNA are joined together in the middle where the bases are. So this would be the base part of it again, right? Each base sticks out into the middle across from the base on the other strand, and they will bond together. And there's a pattern to how this bonding works, which is what I'm showing you with the letters I put on the nucleotides. G always bonds to C, and A always bonds to T. So we have a pattern here, okay? And the binding of the bases in the middle, in there, is what would hold the 2 strands of DNA together. And when you build this together, it looks like a ladder, doesn't it? Sure it does. Well, our rungs are in the middle in here, and then the base of the ladder, I don't know what you call it, the upright part, that's over here. But then these guys the 2 DNA strands do not just lay together flat like this, right? They're actually twisted around one another. And for that, we have to use a rubber band, because they twist around one another like a spiral staircase, which is why DNA is called a double helix. Double-stranded, and it's a double helix. So now if we imagine this guy right here being our DNA, I just am not showing the bases in the middle, right? And then if we take it and do this to it, now we have two strands wrapped around one another, right? Twisted around like a spiral staircase. And that's why they call it a double helix. And that's the structure it would take with those bases in the middle bonded together that hold the two strands together. And here's a 2D image of a very small piece of DNA. Notice we have two strands. This over here on this side would be one strand, and this over here on this side would be the other strand. And that, give it with our rungs in the middle, where G and C are bonded to one another, right? And A and T are bonded to one another, giving us the appearance of a ladder. And this image, this is what we're looking at here in 2D, would be if we laid the DNA out flat, so it's not twisted in this image in its helical shape. And then we have the sugars and phosphates creating the vertical backbone, the sugar, phosphate, right? And then the same thing on the other side. They create the vertical backbone of the ladder, and the bases, like I already showed you, the G, C, A, and T, they're sticking out in the middle, creating the rungs. So the backbone is repeating units of sugar, then phosphate, etc. And the bases bind with each other, or base pair with each other, in the middle as the rungs. Now, notice how A is on the one strand, and it's bound to T on the other. So every time you have an A on one, you're going to find a T on the other, and vice versa. And it's the same thing with G and C. G and C will always be across from one another, bonded to each other. And the base pairing in the middle happens using hydrogen bonds. That's what I'm showing with these dots and dashed lines right here. Those are representing hydrogen bonds. The hydrogen bonds that hold the bases together are found between the bases, and notice that there's a different number of them with G and C as there is with A and T. So let me get to that here in a second. First of all, let me remind you, all the other bonds are covalent in the rest of the molecule, and then you have the hydrogen bonds between the bases. A hydrogen bond is the interaction of a hydrogen atom and an electronegative atom, like a nitrogen or an oxygen, of another molecule or chemical group. The hydrogen must also be covalently bonded to another electronegative atom to create the hydrogen bond. So electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. So the higher it is, in essence, the higher electronegativity is, the stronger it pulls on electrons. And notice how, as I was saying, A bonds to T with 2 of these hydrogen bonds, and C and G with 3 of these hydrogen bonds. That means that the hydrogen bonding between G and C is stronger than it is between A and T, because we have 50% more strength in the bonds. So folks, please get this. I cannot stress this enough. DNA is basically 2 covalently bonded molecules held together in the middle by hydrogen bonds. But the hydrogen bonds aren't nearly as strong as the covalent bonds found throughout the rest of the DNA molecule. This is absolutely critical to understand. Okay, so let me come back to the Legos with this. All right, here we have our Legos again. So let's say, to give you an idea of the bond strength and what I'm talking about, let's say that this is a metal ladder. And the backbone, all this part over here, right, that's all held together by welds. But then the bases in the middle, they would be held together by magnets. So the point here is these welds, all these bonds all through here, and of course this side too, they're going to be a whole lot stronger than the magnets that would be attracting the two and holding the two together in the middle. Furthermore, all of these covalent bonds, again, the welds in a metal ladder, they are all required for the integrity of the molecule. Therefore, if the covalent bonds keeping the two vertical halves of the DNA were broken, it would destroy the DNA. And I can just show you by this, right? If I break these bonds, if I can, I put them together really good. Anyway, if I break these bonds, it destroys it, right? Okay. But then you have the hydrogen bond, which I'm talking about would be as magnets. They're weaker than these. And these bonds in the middle here, these hydrogen bonds, are not required to maintain the integrity of the molecule. They can be broken, the two halves separated, brought back together over and over again. I can do this all day. I'm not tired. Actually, I am. But we can do this all day. And DNA can be opened like this, have these bonds broken and close back up again. It does not destroy the integrity of the molecule. You still would have two intact strands of DNA if you break those hydrogen bonds, okay? All right, let me put these away for a while. So I'm stressing all this because what I want to make the point of is life depends on the structure of DNA. In order for DNA to function, in order to get the information that life depends on out of DNA, you have to be able to open it up and get to the information in the middle of the molecule. You must be able to access the information that's contained in the bases. Life depends on the ability of DNA to be opened up, have its information accessed, which is in the middle, close back up again without being destroyed or altered. And this is absolutely dependent, completely dependent on the structure of DNA. So without this structure, that can't happen. And therefore, life cannot happen. And as you look at the structure of DNA, what you see, what I want to point out here, is patterns. You see patterns all over the structure of DNA. And remember the video where I was talking about SETI and the design inference, right? Patterns tell us that intelligence and prescience were involved in the design and the creation of the DNA molecule. Randomness, the hallmark of evolution, would not and could not create a molecule with so much pattern in its structure. It would not and could not because randomness is random. And the first and most obvious pattern that we see in the structure of DNA is in the base pairing. Like I said, A always bonds with T and vice versa with 2 hydrogen bonds, and G always bonds with C and vice versa with 3 hydrogen bonds. Randomness would not match these bases in such a pattern. There would be a random arrangement to the bases on each strand. And without this pattern of base pairing, DNA is no longer reproducible. Its life essential information is gone. Its functions are completely lost, and therefore, life is lost. And I'll explain more about why this is so when I discuss the functions of DNA. But that's not the only pattern we see in DNA. Like I said, there's a lot more. But in the interest of time, I'm going to end this video at this point, and I'll pick it up from here in the next video. So come on back for that. And if you like what you hear, give me a thumbs up and subscribe to my channel. Thank you very much for watching, and as always, we'll keep the light on for you.